So I hope that everyone has access to Cyclone. So today we'll see how to serve a model through vLLM, and then we will see a couple of RAG pipelines that increase in complexity per se. So the first thing we need to do is SSH into Cyclone. There we go. And if you type ll, you should see a directory called data edu29. What I want you to do is type, let me clear the screen, / data edu29, and then launch notebook. So go ahead and run this command. Make sure you're at your home directory. Do not go into any directories. And then you should see this message right here. If we type sq-me, you'll probably see only one job, which is this one. And it will take a while to load up. The other 3 jobs that you see are actually the vLLM server running. So until everyone starts the notebook, I'll go ahead and show you the script on how to launch vLLM. So for Cyclone specifically, let me go ahead and zoom a bit. Right. I don't know. Is it better? What about this? Default. I don't know if I have a white. Ah, there we go. All right. Okay, perfect. Sorry about that. All right, so this is the script. By the way, all the scripts and notebooks will be available on the GitHub after the training event. So this is the script that launches the LLM that we will talk to. And at the beginning of the script, we have basically the configuration for Cyclone, what the resources that we are requesting. So for our LLM, we need 2 GPUs and 20 CPU cores. And basically, we will launch one task on a single node. For today, we will use only one node, which has 4 GPUs. 2 of them will be used by the LLM. The other will be used for the embedder, and the other will be used for the re-ranker, which we will see at the last notebook. Either way, this is basically the configuration. Then we have to activate the virtual environment for vLLM. This output file is needed so the notebooks can actually talk to vLLM. We need a host name. We need a random port. This is the directory that we will download the Hugging Face model. This is the model that we will be using, Llama 3.08 billion instruct model. You can use any Hugging Face model that you want. The tensor parallel size is a parameter of vLLM that lets you use parallelism. So if you have multiple GPUs, you can utilize all of them. So we tell it to basically use the GPUs that we allocated above, which is 2. This is for some logging. And then we need an API key. Now, the API key might look silly, but it's internal, so it doesn't really matter. And at the end of the day, this is the output that we will have so the notebooks will be able to connect. So again, we have the port, we have the host, the URL, and the API key and the model name. We will see these parameters in the notebook. So finally, what we have is vLLM serve, the model that we want to serve, the task of the model, which is to generate text. Again, the parallel size, we see it's our GPU number, some other miscellaneous parameters, the data type of the model. I limited the model's length, so it will be easier for a lot of users to try it out, so we don't request a lot of resources from Cyclone. It doesn't matter for our use case today because the data set is really small. And finally, we expose the API key, host, and port. So all three scripts are pretty similar, except we are changing the model name and some model parameters here. The same for the re-ranker. And once we have every script ready, we can go ahead and run it. And you will see all the jobs running here. So each one of these is serving, it's a vLLM server, basically. Yeah. For some models, yes, you need to request access for the model, like for Llama 3.0 8 billion, you need to request access from the owner's repository. All right, so the Jupyter job, now it's ready. This is, that's why it says R here, and here it was configuring, basically. So if anyone else doesn't see the R at their job, give it a little while. If you do have the R here, that means it's ready. And if you look into your repository again, typing LL, you should see a directory called RAG training. So I'll go ahead and go into this directory. I want you to follow along, and I'll take a small pause here so anyone can catch up. Is everyone here fine so far? Nice. And anyone online? So we'll take like a 3-minute break so everyone can catch up. Perfect. I see from people online that the job is running. All right, I will continue, and we can come back to it if anyone else is having problems. So while you're inside the RAG training directory, I want you to type LL again, and you should see connection info.txt. All right, so this is important. What we want to do, it's type cut connection info.txt, and you'll see this output right here. So we can see three things here. Basically, to access Cyclone from your computer, we need to establish a tunnel with this command. So I need you to copy it and open a separate terminal that's not connected on Cyclone. So as you can see, the terminal I opened now, it's on my computer. And I want you to type that command in and hit enter. This command will not output anything, and it will stay running like that. That's normal. So once again, cat connection info.txt while you're inside rack training. And then you copy this command right here and paste it into a separate terminal on your system. So once you do that, you need to copy the password for the notebook. And then what you need to do is open your browser and copy this URL right here. And it should open the Jupyter server right here, asking for a password. Go ahead and type the password. And you should have access to all the notebooks that we will be using today. So I'll go over it one more time. So what you need to do is you need to be inside the rack training directory that is found under your home directory. Then you should type cat connection info doc.txt, and you'll see this information right here. Go ahead and copy this command, open a new terminal that's not connected on Cyclone, paste the command right here, and nothing else should happen. It should stay like that, don't worry about it. And after that, you need to copy your password and then open this URL and paste your password, and you should be good to go. I'll wait a few minutes. Yeah. If some people are having connection refused error when they type SSH, make sure that the sq command --me shows R right here and not CF. And if it shows CF, that means that the job did not start yet. So this information right here won't be accurate. So what you need to do is once you see that this is R, then you go ahead and type cat connection to get the refreshed information that will work. Give us a few more minutes so everyone can catch up, and we'll start with the first notebook. All right, everyone, sorry for the delay. All right, so now that we have access to our Jupyter server, let's go ahead and open the first notebook called RAG Basic 01. And I want everyone to make sure that on the top right corner, you see RAG Training VNV. If you don't see it, I need you to click on it. And right here, select RAG Training VNV and set it to always start the preferred kernel and then click select. Perfect. So In this notebook, we will start with the very basics. First, a small introduction to Haystack. Basically, Haystack, it's an AI framework that you can create RAG applications, agentic applications, generally anything that has to do with LLMs, you can do with Haystack. It's a fairly new framework, and that's generally good because it's not that bloated. You can see the website here. It's fully open sourced, and it integrates with many more frameworks that will be useful down the line. So the first step we need to do is actually import our packages. This will take a while. Don't worry about this warning. So let's initialize some helper functions, and then we will establish our LLM config. This config, if we actually look into it, it basically contains all the connection info for our LLM. So then we will see an introduction on the Haystack document data class. So this data class basically contains all our documents, their content, some metadata, some scores, their embeddings, their sparse embeddings. It contains basically various information about the documents that we want to perform RAG on. So here we have a directory that contains our documents, and we use a converter which is found in the helper function. Basically, we use a converter from Haystack, which converts docx documents to Haystack documents. So, and for the document store, we will not use a vector database yet. We will just store the documents in the system's memory. So let's go and run this. All right. And we can see, we can check what the document looks like. So first of all, as you can tell, the type, it's basically a document data class, and it has a unique ID. This is the content of our document. Basically, the documents for this training event, it's like various policies of a company, some events. Basically, imagine that your company has a chatbot and you want to talk to it. So this document, it's about the company hackathon, apparently. And you can see all the content right here. This is stored again in the documents data class. We can see some metadata again that's automatically generated from Haystack. So you can see the author, then the file path, some information about when it was created, who modified it last, and so on and so on. So now that we have our documents, we have the converter ready, we need to start indexing those documents. If you remember from Chris' presentation, this is the first step. You have the documents, you extract some content from this document, which is the text, and then you create some embeddings, and then you store them in a vector database. In our case, we won't do that yet. So, but before we index our documents, we have to split them in chunks. And then there are various reasons on why it's that. The first reason is that our models have a limited capacity on how much data they can process. So if we have a very, very long document, it might exceed that context window and throw an error. The other reason is that, let's imagine that we have a document that spans 35 pages, but the relevant information that we want from our query, it's found only on page 5. So why load the whole document to the LLM with useless information instead of loading the most relevant chunk? And of course, this again, we can expand this this argument by saying, okay, let's imagine that to answer our query, the LLM has to access a lot of documents. So what I'm trying to say is making splitting the documents into smaller chunks is more efficient, and it also helps reducing hallucinations because you don't feed the LLM with useless information. The goal of the LLM is to answer the user's query. So let's play a bit with the tokenizers. So right here, we will use a tokenizer from the pre-trained model BGE M3. And we will calculate the tokens for the first document, and we will calculate the tokens for the first 500 characters, basically. So you can see the token count, it's 125, and you can actually see the tokens themselves. You can observe that some words get split, like hackathon gets split to hackathon. And let's say we want to see the whole document, how many tokens it has. Let's place -1 there. So the whole token is 1,200 tokens. So if our embedding model had a max capacity of 512, we wouldn't be able to load this document into it. So this is the first reason on why we chunk our documents. So another thing you want to consider is, now let's use a different tokenizer from this model right here. Let's calculate again the tokens for the 500 characters from the first tokenizer. We get 125 tokens. Now let's tokenize the same content with the other tokenizer, and you can see the token count is different. This is because each tokenizer uses different tokenization methods. You can see on the second tokenizer, the words get split differently. So for hackathon, this time we have hackathon. And also, when it splits the word, the character of the split, it's different. And let's try to tokenize the whole document for the second tokenizer as well. And you can see this warning right here. So this warning basically tells us that the maximum sequence length for this model right here, basically, it's 512, but the document we are trying to tokenize, it's more. So basically it's telling, if you run this through the model, it won't go well. So the main takeaway from this is, if you are going to use a tokenizer, use the tokenizer that was used for the model, for the embedding model that you are planning to run. So let's initialize the document splitter. We actually initialized it above. Let's run the document splitter. And for this notebook, we will, hello. Okay, my notebook, it's a bit, okay, it's running, sorry. So what we see right here, First, we split the documents into chunks. And then, like I said, for this notebook, we will be serving only the LLM with vLLM. So our embedding model, the dog embedder right here, it's actually running inference using Torch, which is very inefficient and slow compared to vLLM. And you can see here that the inference time took 7 seconds, 7 seconds basically. And we stored 400 documents. Now, when we say documents, we mean document chunks. So we calculate the docs with the embeddings on this step right here. And then we write the documents to our documents store. Now we can access these documents. Then we can initialize our RAG pipeline. So specifically, we have a prompt template, to be precise. We can check the prompt template right here. As you can see, it has a task, it has some guidelines, and it has some added information right here. So when you send a query to an LLM using this pipeline right here, it will first read the task, then it will read these pipelines guidelines here, then it will read the conversation history, then the actual source context, which is basically our documents. Then it will read the user query before answering. So the components that we need to run this RAG pipeline, it's basically a text embedder. Like I said, when we send a prompt, a query to the LLM, we need to turn it into an embedding. This is how we calculate the similarity with the stored embeddings. So let me go ahead and, whoop. So yeah, we need a text embedder to actually calculate the embeddings. We need a retriever, which will basically retrieve relevant documents from our document store based on our query. Then we need a chat generator, which is basically our LLM. And you can see here for the LLM, we are using, vLLM basically uses an OpenAI compatible API key. So we can use Haystack's OpenAI chat generator method, but instead of putting the API key and base URL of OpenAI, we can put the API key and URL of vLLM. So with this code right here, we can talk to vLLM. Then we have the prompt builder. Basically, it creates the prompt for the LLM. And then we can establish our actual RAG pipeline. When we establish the pipeline, we can add the components like the text embedder, the retriever, the builder, and the LLM. And then we have to define the outputs and inputs of each component. So the text embedder will output embeddings, so the embeddings of our query. The retriever will take those query embeddings and output the relevant retrieved documents, and it will send them to the prompt builder as documents, and the prompt builder will output a prompt, and it will send that prompt to the LLM as a message. Yep. Cosine similarity, that's how it decides. But yeah, it basically, it's, where is it? Whoop. Oh, here it is. So the retrieval will basically perform this. The content, which is our documents, and the query get turned into vector embeddings. The content is actually stored in the vector database, not the query. So the retrieval will retrieve some relevant documents from the vector database and send it back to the application. Oh, yeah. So what's happening here, basically, this is an example of what's going on. We have the content here, which is our document chunks, and they go through the embedding model, and they are turned into vector embeddings, and they are stored into the vector database. So when a query comes in, it will pass through the embedding model again. It will get turned into a vector embedding, and the vector embedding of the query will get, the retrieval will basically calculate a cosine similarity between the vector embedding of the query and the stored embeddings that we have in the vector database. And the query result is basically the retrieved documents. So this is what happens here. The text embedder is calculating the embeddings of the query, and the retrieval will retrieve documents based on how similar these documents are to the query. Yeah. Mm-hmm. Yes. Okay. No, you don't have to re-embed everything if you want to add to the vector database. Basically, a vector database, you can run SQL commands. So you can have an SQL command that retrieves the already embedded documents, and you can add the new ones to a list and embed only those, basically, and add them to the vector database. No, no. One key thing here is that you always have to use the same embedder that you used in the indexing phase. So this embedder has to be the same embedder that you used when you indexed your documents. This is because you want the embeddings to fall into the same vector space or so. You want them to be similar in structure, I guess, something like that. Anyway, feel free to ask any questions, by the way. Now that we have the pipeline ready, we can come down below. This is an overview of the documents that we have in the document store. So we have like a document about the new office layout plan, some product documents, and so on. And we can ask a question to the LLM. And we will get back a response. Now, the question was, I'm a new employee, onboard me about the Quantum Stream product. When we get all that. This is all fictional, by the way. ChatGPT generated the documents. So this is it about the first notebook. It's the second notebook will be pretty similar, but the main difference is this time we will be using the embedder from vLLM. So now we are serving two models instead of one. We will play more with the LLMs at a later notebook. So if you want, go ahead and open the next notebook, RAG Basic 02. Like I said, let's import the packages. Let's import some helper functions. And this time we're loading the LLM config and the embedding config. It does take a while to load the packages. So similarly to before, we have the documents. We convert them into haystack documents. We initialize the splitter and we initialize the document store. Again, we are not using a vector database. The vector database will come at the next notebook. But you can see from here that this time the doc embedder, it's initialized by using the OpenAI document embedder method from Haystack. And similarly to the vLLM on the last notebook, we define an API key, an embed URL, and a model name. So let's go ahead and run this. Again, we can see some, if we run the cell below, we can see some content of our documents like before. We can check the tokens as well, but this time we will see why splitting the documents is important. So the token count for the whole document, let me change to -1, is again 1203. Now, if we split the documents by running the splitter and checking the chunk, we can see the splitter adds a few keys here. First of all, we can see the file name. Again, we can see the metadata, how many pages, and where does the split end and start. If we change the chunk index to like 3, you can see that the file path is the same. This is because this document right here, the annual hackathon announcement document, was split into multiple chunks. I'm not sure how many, let's put like 15 here. It's still the same document, so we have a lot of chunks for this particular document. And we can calculate the tokens. The token count for this particular chunk, it's 31 tokens. Now we can go ahead and run the indexing phase again. And this time, instead of 7 seconds, it took 2 seconds to calculate all the embeddings for 400 document chunks. And this is by only running on a single GPU. You can see that the difference is it's very big and it scales up, especially if you have 1,000 or millions of documents and very large documents. So similarly to before, we establish the rack template, that it's the exact same template from the last notebook. We use, again, the text embedder is now established through vLLM. So now you can see we have 2 models here instead of 1 that use vLLM. Let's go ahead and use this. All good. And now we can again run a few queries. And again, we get back a response. Now, I have, how much time do I have? 1 hour, perfect. Let's go to the next notebook. All right. Now let's check the vector databases. Also, let me try to hide the floating things. Nice. So now let's utilize a vector database. For this notebook, we will use the Milvus vector database. We used it on various projects and it's really good. Let's import the packages again. Let's run a few helper functions. Let's set up the vLLM connection parameters. And now let me zoom in. Now we initialize the vector database. So what we need here, basically a connection argument, which is basically where it will download the. Okay, let me start from the beginning. Milvus has two modes, let's say. You can run Milvus Lite, which is like this. You install it with pip install and it's ready to go. Or you can run Milvus in distributed version. So you can run Milvus on Cyclone, for example, and you can have it process thousands and millions of documents. For our use case, we will use the light version, and because it's not hosted anywhere, it will basically create a .db file in your directory. And this is where the documents will be stored when you index them. So this is what we put in the URI here. Yeah. It's the vector database. It's what stores the documents. You can retrieve documents through Milvus. You run indexing. Yeah. You can check Milvus. This is the website for Milvus, basically. And again, this is open sourced as well. So let's initialize our document store with Milvus document store. Again, this is an integration of Haystack. I'm not sure if this is a warning, so it should be good. All right, let's go to the indexing components. Again, we have our documents, and we have the doc embedder like before, and the splitter. Let's go ahead and initialize them as well. And now we have the indexing pipeline. And now we have a few more components here. First of all, we have the converter. We did have the converter before as well, but this time we are not running it separately. We are running it inside the pipeline, and this is why you see it here. Then we have the document cleaner, which basically does what it says. It removes extra white spaces. It removes duplicate headings, white lines, empty lines. It does some basic cleaning. Then we have the splitter that we saw before, the document embedder, and the document writer. So let's go ahead and run this pipeline. So we calculated 397 document chunks. This is the total tokens that we generated. And now everything is saved inside our vector database. So now that we have this vector database, we can test the retrieval. So again, every prompt has to turn into an embedding. So right here, we have a dummy text embedder that uses vLLM. And we have this question, tell me a bit about quantum stream. And we have a Milvus embedding retriever that will retrieve the three most similar documents. So if we run this, you can see the three chunks that it returned. So remember, we asked it something about quantum stream, and the document chunks that we got before are all relevant about quantum stream. So this is how the retrieval basically works. This cell right here is basically this right here. All right, so now that we saw how the retrieval works, let's initialize our RAG pipeline. Again, we have a prompt template. And then we have the components. We have the chat generator, which is basically the LLM, and the text embedder, like before. And this time the retriever changed as well. Now it's a Milvus embedding retriever instead of in-memory embedding retriever or whatever it's called. So let's initialize the pipeline and let's perform some RAG. Here we go. So again, everything works together. It retrieves relevant information. Again, this is subjective to your data and how you process your data. If you have data that's very complex and unstructured, you might need to pre-process it a bit more, which we will see in the next notebook. Let's go ahead and try the new notebook, the next notebook right now. But first, what I want you to do, I want you to click on kernel. This is very important because it will break Milvus if you don't. I want you to click on kernel and I want you to restart the kernel. The reason is when we initialize Milvus right here, in the next notebook that we will use, we will have the same code. So when we try to initialize another document store with the same URI right here, it will basically throw an error telling us that there's already an open connection to that database. So we restart the notebook so we break that connection. So let's close everything and get to the advanced notebook. All right. So in this notebook, we will add a few more features, let's say, to our RAG pipeline. And by the way, every single code that we will see here, it's what's running on Open Web UI, which I will show later on. This is hosted here at the Cyprus Institute. So basically what we will do in this notebook is, of course, import our packages. Let's import some helper functions as well. And now we have 3 models that we will serve with vLLM. We have the actual LLM, we have the embedding model, and now we have a re-ranker. The re-ranker, I will keep it short because we don't want to run out of time. The re-ranker does this. So we have a retriever that retrieves documents. Let's say that the retriever retrieved these relevant documents. But because the retriever works on cosine similarity and it works on the embeddings, there's always a bit of information loss. So what the re-ranker does, it takes these 25 documents and re-ranks them and outputs the most relevant, in this case, the top 4 most relevant tokens. This is very useful because you're boosting the quality of the information that you pass into the LLM. And also, you don't have to load 25 documents here into the LLM. You can load 4, which in some cases might be enough. So you don't need that, you don't use that much context. Anyway, we'll see it in the notebook as well. And the other thing that I will introduce you to, it's called DocLink. This is, of course, another open sourced framework. It's basically a document parser. Wrong link. So this is a content extraction framework, basically. What it does, it works with multiple file formats like PDFs, HTML5 files, Word document files, and it outputs their content in in a structured way, and it also performs chunking for us. So let's test it out. Let's run this cell to load our files. And what we will do, it's called hybrid chunking from Docklink. Basically, the chunking method works in 2 steps. Docklink will first analyze the structure of the document and perform chunking on that. And then it will take it a step further, and it will use a tokenizer to split the chunks even more using the tokenizer. What this means is that if you have a paragraph and you want to chunk it, using a tokenizer, it will make sure that the paragraph won't get split in half. So all of your chunks are a bit more cohesive. So let's go ahead and test it out. We initialize the embedding model, which is something I forgot to do. I forgot to run this one, sorry. So make sure to load the connection parameters, run the cells again. Nice. So what we have here is, again, the Docklink converter. And for the chunking parameter, we use a hybrid chunker with the tokenizer from our embedding model. And for the documents, we won't run it on our documents. We will actually input a URL. This might take a bit to run, at least for the first time, because it downloads a couple of models on its own, because it performs OCR as well. So it needs to download these models. Let's give it a while. This is an opportunity to ask any questions if you want. This is a warning because Docklink was updated recently and they forgot to remove this argument, but they did add the check to say that it's depreciated, so feel free to ignore it. And now let's inspect a chunk. You can change the ID here, but let's check the chunk with ID 2. And we can see all of this was done automatically by Docklink. We can see the heading. We can see the content, of course. And we can see some metadata. We can see that this is a text. We can see that it's a part of the body. We can see that it doesn't have any children. We can see the page number, the bounding box on the PDF, the character span. Basically, we can see a lot of metadata that can be useful to the LLM sometimes. For example, we can pass this metadata to the LLM, and the LLM, when it references a chunk, it will know which chunk, which file, which page. So basically, it can write citations for you. All right, so let's establish our vector database again. This is the same warning than before. If you get an error here, you have to go back to the vector database notebook and restart the notebook. And then we will establish our indexing pipeline like before, but this time it's a lot smaller and simpler. We have the doc embedder, and then we only have 3 components now instead of 5. We have the converter, which is Docklink, the embedder, and the writer. We don't have the cleaner, we don't have the splitter And this is because Doglin will handle all that on its own. And you can see here, for the Doglin converter, we have max tokens 256. This doesn't mean that every chunk will be 256 tokens. It's an upper limit. Some chunks might be 60 tokens, some chunks might be 200 tokens. But the max limit will be 256. So let's run the pipeline. We index our documents. And now instead of having 400 document chunks, we have only 59. The prompt tokens are, I think, are around the same. And now we can continue. Not sure what this. Okay, I ran the cell by mistake again. Ignore this error. Let's go basic arguments for our LLM. So another feature that we will use in these RAG pipelines is it's a query rephrase LLM. So for your RAG application, you have the LLM that you send queries, but you can have smaller LLMs performing smaller tasks. In this case, we have a query rephrase model that will take the query of the user and try to rephrase it in a way that provides more context to the actual LLM. And the task for the query rephrase is this. You are given a user query and the conversation history, and your job is to rephrase the query only if necessary following these rules. And we have some guidelines, and similarly to before, it needs the conversation history and the user history query, and then it will output the final query. So because we have another LLM, we need another prompt builder as well. Then we need the actual query rephrase LLM that will perform the rephrasing. This is a helper function to help us link the connections for each component. Again, we have the text embedder like before. We have the retriever like before. And now we have the ranker that I explained earlier. Then we have another prompt builder for the final LLM, the actual LLM. And then we have a couple of components that control the conversation history, basically the memory of the LLM. So let's go ahead and initialize all our models and initialize the re-ranker as well. And then we will initialize the pipeline. So again, for the pipeline, we have the prompt builder, the query rephrase LLM, the text embedder, the retriever, the re-ranker, everything that I mentioned so far. You can see that the pipeline gets quite large. And then we have to connect the inputs and the outputs of each component right here. So let's go ahead and run this. And all good. Ignore this warning. So finally, we can start talking to our LLM. So because now we have the conversation history and there are a lot of users, in order to avoid draining too many resources of Cyclone, I have the memory to store only 4 messages. So let's go again and run this question right here. Let's give it a while. So the question was, I am a new employee at the company, onboard me about the Quantum Stream product. And the search query, it's the same. So the query rephrase LLM did not change anything because the prompt itself was fine. It didn't need any changing. It didn't contain any typos. And if we go a bit below, we can see the re-ranked documents. So we can see the scores. For the first document, the score is like 32%, and this is the content. Feel free to look around, change the index here to look at the values. All right, don't go above 5. To look at the values, oh yeah, because I have it to retrieve the top 5, so 4 is the last index. And you can see the last retrieved document only has 10% similarity. Oops. All right, I just closed my notebook. So, we can go ahead and ask something else. So, let's say that we are an employee and we want to ask, do I have to attend to the hackathon event? Let's go ahead and run it. Blah, blah. It's saying something. Basically, let me go ahead and reset the memory. All right. So now we asked it if we want to attend the hackathon event, and because it is now stored in its memory, we can go ahead and ask it, will I get any penalties if I don't attend? And now it should make the correlation that we are talking about the hackathon. Yep. And also, you can see I have a minor typo here. I'm missing an apostrophe, and the LLM did add that. You can go ahead and play with it, run a few prompts. The list of the documents, it's up here. So you can ask, you can play a bit and ask any questions if you want. This is the last notebook, by the way. So we have a bit of time for discussion. And also for anyone online, feel free to ask as well. And again, all this code and the vLLM scripts and the notebook that Nikos showed at the beginning, all will be inside the Git repository that we shared, and we will share it again. Yeah, of course. Yeah. Mm-hmm. So everything that we showed today will be uploaded to the GitHub repository. Since we have a bit of time, I can go ahead and show you Open Web UI. This is, again, an open source interface that you can use it to talk with LLMs and perform RAG. And the exact code that I showed you on the last notebook is what it's running behind this HR assistant. You can select a lot of models, especially if you have an OpenAI API key, you have access to all their models. But in our case, we are using a custom RAG pipeline, and we can start talking to the LLM. which is a bit slow. It's a prototype. So here we can ask it, about the new office layout and if we're losing our desks. And it should hopefully answer correctly. And again, at the backend, all the code that's running, it's what I showed a few minutes ago. We are using Milvus, we are using a re-ranker, we are using a query rephraser. And this is another feature that I showed. We are telling the LLM in the RAG template to also cite which documents it's taking information for. The reason that chapter and page is not available, it's because it's how I created the documents. But generally it's working, so you can see this information comes from this document, same here. So you can have citations. And it works really well. The user experience, it's pretty similar to ChatGPT, the interface, I mean. You have all your chats, you have some settings, you have a profile, you have a lot of features, basically. It can be a training event on its own. But yeah, this is it from me. If you have any questions, feel free to ask. And thank you for coming. Please, do you have any questions online? No, this is an internal tool for prototyping and playing around. Yeah. Like a hardware architecture. For the hardware, what dictates your hardware? It's first of all your budget, obviously, and then what models you need to run. For example, the new open weight models from OpenAI require, I think, CUDA Compute 9. So you need a fairly new-ish GPU architecture. If you have like a V100, you cannot run those models. And also depends on how large your models are. If you want to run very large models, you need to go with GPUs that are more on the higher end. Yeah. Yes. Yes. Mm-hmm. Exactly. Sometimes yes, sometimes no. It depends. Milvus is just the vector database. It doesn't control the chunking. What controls the chunking is, let me go up. No, it's the docklink converter. Yes. So the docklink yes. So sort of. You can put a hard limit, which is 256 in this case. So no chunk will go above that, but the size of the chunks themselves, you can't really control that easily, because for some chunks, it might make sense to be 60 tokens, because let's say it's a small sentence. So you want to chunk that sentence only. For other chunk that it's a paragraph, you might want it to include that paragraph into a chunk. So it might be 130 tokens. So this is the reason we use the hybrid chunker. So it's basically this right here. the content extractor, which is docling in this case, will first find the sections of the document. So a paragraph, some tables, another paragraph, which is this. And then it will take each one of them and chunk them even further using a tokenizer. So this paragraph might be split into 3 chunks, let's say. Yes, if you use hybrid chunking, it basically it ensures that the chunks will be concise and consistent in terms of what information they contain, because you won't have a chunk that it's split in the middle. So you have a sentence split in the middle and the rest of the sentence it's in another chunk. So in this case, if it was like this, you wouldn't. Yes, but at the first stage, yes. And this is why we perform token-aware split. What do you mean by the first? It's 2 stages, but the final output it's this. Yeah, this is what will get stored into your vector database, the red part. This is just internal to Dockling. Yes, imagine it in steps of the process, basically. But at the end of the day, this is what you will get. So in the case that you have a paragraph or a sentence that gets split in the middle into 2 different chunks, when you want to load that sentence because it contains relevant information, you need to load 2 chunks instead of 1. So that's inefficient. So that's the main reason why you would use a hybrid chunker. And for the re-ranking part that I mentioned before, basically, when you first, let me see if I can find it right here. So this right here, it's the first retrieval part here with cosine similarity, just a similarity between numbers, basically. So because it is between it's between numbers, it's very easy computationally. It's not that hard. This is why you can retrieve a lot of documents, 25, let's say. But because it's when you turn a text into an embedding, there's a bit of information loss because you compress the text, the semantic meaning of that text into a specific dimensional vector. So when you retrieve these documents using cosine similarity, the retrieval might also retrieve documents that are not that similar. And also the most similar documents might end up down below because of how the embeddings were calculated. So what you want to do also, let's say that your model cannot handle 25 documents. So what the re-ranker does, it takes those 25 documents and semantically re-ranks them again. It's a heavy operation, computationally heavy, but you make up for it in the end by giving your LLM more clear context. It's not that useless information that might come through. But again, the general rule of thumb, you start small from our basic pipelines and add to it, because at the end of the day, you might not need a query rephrase LLM, a re-ranker, a hybrid chunker, and all this fancy stuff. You don't have to go straight to the advanced. You go slowly. Yeah. If the SSH command asks for a password instead of a passphrase, that means that something happened with the SSH key. Yeah. Oh yeah. What you can do is you can put on the SSH command, you can put -i and put the actual private key there, the path. Oh. Generally, when we do these training events, we dedicate 30 minutes at the start of the event so everyone can sort these issues out. I guess what you can do if you don't have access to Cyclone, you can use these notebooks on Google Colab that gives you access to a GPU. But of course, you won't have the vLLM running. But in reality, you don't really need it for this kind of, for these notebooks at least. Yeah, but those notebooks, I think, required an OpenAI key. But yeah, we have another repository that has some RAG notebooks. You can run those on Google Colab as well. I will put the link in the repository of this training event. But for that event, you need an OpenAI API key. Yeah. So if no one else has any questions, I'm not sure. Let me check online real quick. Yeah, of course. Yeah. No, the split happens using a tokenizer, basically. That's defined by the tokenizer. Oh, sorry? But are you talking about this Dockling split? It will split the chunk. So we have this right here, let's say. It will use the tokenizer to actually tokenize this whole thing. And how exactly it will decide where to split and what, I'm not quite sure. But yeah, at the end of the day, what Dockling does, when it finishes with all the chunking, it will go over all the chunks and actually modify them in some way to make bigger chunks smaller to fit our defined size and to make smaller chunks a bit bigger so we don't have a lot of small chunks, which also can be inefficient. Yeah, in some way, yeah. 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 Generally, you want to use the tokenizer that was used for your embedding model. So the tokenization of the chunks, it's what was your embedding model was trained on. So the input of the data, it's similar. Generally, you start with the tokenizer that your model was trained on, but that's not a hard limitation. You can try a different tokenizer. It probably won't make a big difference. Depends on your data, of course. If you would like to run this code again, you won't have access to Cyclone after a while. So if you are going to run it on Google Colab or your personal computer, you will have to change the code a bit here, because when it's going to run this code, it won't be able to access this API key and embedding URL. So you will either replace this method, the OpenAI document embedder, replace it with something else, a different embedder. So if you go to Haystack document embedders, you can see we have an embedder for Amazon Bedrock if you're using AWS. We have Azure OpenAI if you're using Azure. There's probably a Hugging Face API document embedder if you're using Hugging Face. So go into Haystack and read the documentation. But at the end of the day, if you're going to use this code on Google Colab, you will have to change the document embedder and any other LLM or the re-ranker. Basically, any connection that you see that points to vLLM, you'll have to change it. Unless you launch vLLM on your computer, which is technically possible. I mean, it's not something heavy. And what else? If you do have an OpenAI API key, you can leave this method right here, the OpenAI document embedder, and just change the API key here. So that will work. But yeah, Haystack has integrations with a lot of very known frameworks for connections as well with GitHub. So you can grab files from GitHub with classifiers. You can build agents with Haystack. It's a great framework. All right. If that's all, thank you, everyone. Feel free to send me an email if you have any questions, or if you're here, find me outside and we'll have a talk. Again, thank you for coming, and have a lovely day.